Welcome to the Deep Dive. We take stacks of information, sometimes dense stuff, and boil it down to what you really need to know.
That's the plan.
Today, we're tackling something pretty fundamental, how airplanes actually fly, and just as importantly, the rules that keep everything safe up there.
Right. Our guide for this is the FAA's own Pilot's Handbook of Aeronautical Knowledge, the 2023 edition. It's pretty comprehensive.
It really is. And whether you're maybe thinking about learning to fly, or you're just someone who flies commercially and is curious, we want to give you the key takeaways, quickly, clearly, without drowning you in jargon.
Yeah, hitting the highlights. We'll cover the basics, who makes the rules, the forces involved in flight, how planes are built, even a bit about weather and navigation.
Exactly. So have you ever been sitting on a plane, maybe looking out the window, and just wondered, how is this giant metal tube staying in the air?
It's a good question, and maybe we can shed some light on that today.
Let's do it.
Huh.
So where do we start? Probably with the rule makers.
Makes sense. Before you can fly, you need the framework. And in the U.S., that's mainly the Federal Aviation Administration, the FAA.
Okay, the FAA. Most people probably think of air traffic controllers, right?
Sure, that's a big part of it. But they do way more. Our handbook points out they set standards for aircraft noise, for instance. Think about airports near neighborhoods.
Ah, so environmental stuff too. Didn't realize that.
Yeah, and it's evolved. The handbook mentions they even got involved with regulating high-altitude kite flying way back, and more recently, taking on more responsibility for airport safety programs. It's broad.
High-flying kites. Okay, didn't expect that one. So they set the rules. Where do these rules actually live? Is there like one giant book?
Pretty much. It's called the Code of Federal Regulations, or CFR. Title 14 is the section for aeronautics and space. That's the official rule book for everything from getting a pilot certificate to building an airplane to operating it.
Title 14 CFR.
Yeah.
Got it. That sounds intense. How do people navigate that?
Well, the FAA provides a lot of help. One key resource is the Aeronautical Information Manual, the AM.
The AM. What's its main purpose?
Think of the AIM as the how-to guide for flying in the U.S. airspace system. It explains procedures, radio calls, airport markings, all the operational stuff you need to know to fly safely and interact with the system. Less about the rules, more about the procedures.
Okay, so CFR is the law, AMM is the practical guide, and the handbook we're using today is another resource.
Absolutely. The FAA puts out tons of handbooks like this one, covering everything from basic knowledge to advanced weather flying or instrument procedures. And the great thing, as the handbook notes, is a lot of them, including this one, are free downloads on the FAA website. Figure 115 in the handbook actually shows a whole list of them.
Free is always good. Accessibility matters. What about advisory circulars or ACs? Are they rules too?
Good question. No, ACs are more like informational guides or recommended practices. They might explain how to comply with the regulation or offer safety tips. They're helpful, but not legally binding like the CFR. Some are free, some you pay for, all on the FAA site.
Right. Helpful advice, not hard rules. And flight publications. That sounds like charts and maps.
Exactly. These are the actual documents pilots use for navigation and procedures in flight. Aeronautical charts, airport diagrams, instrument approach procedures, the essential stuff you need in the cockpit.
Makes sense. Then there are NOTAMs notices to airmen. They sound important, maybe time sensitive.
Extremely. NOTAMs contain critical information pilots must know before a flight. Things like temporary runway closures, equipment outages, maybe a construction crane near the airport. They're all about immediate flight safety. Checking NOTAMs is a non-negotiable part of pre-flight planning.
Crucial safety updates.
Okay.
And if pilots need help or clarification on rules or safety?
The handbook mentions aviation safety inspectors, ASIs. They're FAA folks who handle oversight and checks. And there's also the FAA safety team, or FAST team, often volunteers, experienced pilots helping promote safety through seminars and outreach. So there's definitely support available.
Okay, quite a structure supporting aviation safety. Let's shift gears now to the actual flying part. How do these machines get off the ground? The handbook gives a little history lesson first, doesn't it?
It does. It briefly mentions early pioneers like Henson and Lilienthal, who experimented with gliders, and then, of course, the Wright brothers. Their first controlled, sustained, powered flight in 1903. That really kicked things off. You can see pictures of their flyer in the handbook.
A huge moment. But the core physics they figured out still apply today, right? The handbook talks about 4 fundamental forces.
That's right. Lift, weight, thrust, and drag. In steady flight, they're all in balance.
Okay, let's break those down. Lift is the upward force, countering weight. How is it generated? The handbook mentions Bernoulli and Newton.
Two key ideas work together here. First, Bernoulli's principle. Basically, faster moving air has lower pressure. A wing is shaped curved on top, flatter on the bottom so air flows faster over the top.
Faster air on top means lower pressure up there.
Exactly. Lower pressure on top, higher pressure pushing up from below. And that pressure difference creates lift.
Okay, that's Bernoulli. What about Newton?
Newton's third law, action and reaction. The wing is angled slightly, pushing air downwards as it moves forward. This downward push of air, called downwash, creates an equal and opposite upward reaction force on the wing. That's also lift. So it's both the pressure difference and the reaction force working together.
Fascinating. The shape and angle are key. So lift opposes weight gravity pulling down. What about thrust and drag?
Thrust is the forward force from the engine propeller or jet. Drag is the resistance, air trying to hold the aircraft back. Thrust has to overcome drag for the plane to move forward and maintain speed.
And drag comes in different forms. Skin friction and induced drag.
Right. Skin friction is just that friction from air moving over the aircraft's surface, the skin. Even smooth surfaces have microscopic roughness causing drag.
Okay, like air resistance. What's induced drag?
Induced drag is interesting because it's a direct result of producing lift. Remember the high pressure under the wing and low pressure above? Well, at the wingtips, some high-pressure air tries to curl around to the low-pressure area on top.
It spills over the edge.
Sort of, yeah. It creates swirling air masses called wingtip vortices. These vortices disrupt airflow and create drag. The more lift you're making, like at slow speeds during takeoff or landing, the stronger these vortices are, and the higher the induced drag.
So flying itself creates drag, an unavoidable trade-off.
Pretty much. In steady flight, thrust equals drag and lift equals weight. It's all a balance.
Okay, that covers the forces. Now, how are these aircraft actually put together? The handbook defines an aircraft pretty broadly first.
Yeah, basically anything designed for flight. Then it specifies categories like airplane, rotorcraft, that's helicopters, gliders, and so on. An airplane specifically is defined as engine-driven, with fixed wings, relying on airflow over those wings for lift.
Fixed wings are the key for airplanes, and those wings can be attached in different ways: high, mid, low wing.
Correct. High wing, like on many Cessnas, often gives good stability and ground clearance. Low wing, common on airliners and many trainers, can have different aerodynamic properties and landing gear arrangements. Mid-wing is less common, but used on some aerobatic or fighter planes. The handbook shows examples. You also see monoplanes one wing and biplanes with two.
And how are they supported? Some have struts, some don't.
Right. Wings with external braces, or struts, are called semi-cantilever. The struts help carry the load. Wings without external struts, where all the support structure is internal, are called cantilever wings. They look cleaner aerodynamically.
Gotcha. What of the main body, the fuselage? Monocoque and semi-monocoque construction.
Those describe how the fuselage gets its strength. Monocoque is like an eggshell. The outer skin bears the main stress. Think of some older designs or maybe lighter structures.
So the skin is the structure.
Largely, yes, but semi-monocoque is much more common now. It uses the skin to stressed skin, but combines it with an internal framework. You have bulkheads, formers, stringers, like a skeleton inside that reinforces the skin. The handbook shows this well. It makes the structure lighter for its strength and more damage tolerant.
Stronger and lighter. Makes sense. The handbook also mentions the firewall.
Crucial safety feature in single-engine planes. It's a fireproof barrier right behind the engine, separating it from the cockpit and cabin. Very important.
Absolutely. And materials are changing too.
Yeah.
Composites.
Yeah, materials like carbon fiber, fiberglass, aramid, they're strong, lightweight, and don't corrode like aluminum. Big advantages for performance and maintenance. Think of the Boeing 787 Dreamliner, lots of composites. The handbook even mentions their use in stealth aircraft for reduced radar signature.
Lighter, stronger, no rust. Sounds like the future. Okay, so we have a plane built. Knowing how fast it's going is critical. Let's talk airspeed, indicated versus true airspeed.
Right. Indicated airspeed, IAS, is what the gauge in the cockpit reads directly. It's based on air pressure hitting the pitot tube, but air gets thinner higher up, so IAS becomes less representative of your actual speed through the air mass.
So true airspeed, TAS corrects for that.
Exactly. TAS is IAS corrected for altitude and temperature effects on air density. It's your actual speed relative to the air around you, important for navigation planning.
And that gauge, the airspeed indicator, has colors on it. The handbook shows these arcs.
Yes, very important markings. They show the aircraft's operating limits at a glance. There's a white arc for the flap operating range speeds where it's safe to extend flaps, a green arc for the normal operating raise, a yellow arc for caution smooth air only, and a red line, VNE velocity never exceed. You absolutely don't fly faster than that red line.
Color-coded safety limits. Good visual cue.
Yeah.
Now, the handbook talks about stalls. This isn't the engine quitting, right?
No, absolutely not. A stall is an aerodynamic event. It happens when the wing exceeds its critical angle of attack.
Angle of attack. That's the angle between the wing and the oncoming air.
Precisely. If that angle gets too large, the airflow separates from the top surface of the wing and it dramatically loses lift. The key point the handbook makes is that a stall can happen at any airspeed, any attitude. If you exceed that critical angle, it's not just about flying too slow.
So it's the angle, not the speed itself. That's a crucial distinction. What about VA, design maneuvering speed?
VA is the speed below which you can make a full, abrupt control input, like yanking back on the controls without potentially overstressing the airframe. It's important in turbulence or when making sudden maneuvers. But the handbook warns it only protects against one full input at a time, not multiple or combined inputs.
Structural safety speed. And one last thing here. Ground effect.
Yeah.
How does being near the ground change things?
When the aircraft is flying very close to the ground, say, within one wingspan height, the ground interferes with the airflow patterns around the wing. It particularly restricts the formation of those wingtip vortices we talked about.
So it reduces induced drag.
Yes, primarily. It can feel like the airplane wants to float, or that you need less power. It also means the airspeed indicator might read a bit lower than expected just before touchdown. It's most noticeable during takeoff and landing.
Interesting effect near the surface. Okay, let's talk about how pilots actually control the airplane. Primary controls first.
Sure. The three primary flight controls manage rotation around the three axes. Ailerons, usually on the outer part of the wings, control roll banking left or right.
Okay, ailerons for roll.
The elevator, typically on the horizontal tail surface, controls pitch, nose up or nose down.
Elevator for pitch.
And the rudder, on the vertical tail fin, controls yaw, swinging the nose left or right.
Rudder for yaw. Roll, pitch, yaw.
Yeah.
Got it. What about secondary controls? Flaps.
Secondary controls modify lift or drag. Flaps are probably the most common. They extend from the trailing edge of the wing, usually inwards from the ailerons. They increase both lift and drag. Great for allowing slower takeoff and landing speeds.
More lift, more drag. Useful for slow flight. Any others?
Spoilers are panels on the top surface of the wing that can be raised. They spoil the lift and increase drag significantly, used to help slow down, especially after landing, or for steeper descents without gaining speed. Some large aircraft also use them to help with roll control.
Spoilers disrupt lift. And trim systems.
Trim systems are crucial for reducing pilot workload. They allow the pilot to adjust controls so the airplane maintains a desired pitch, roll, or yaw attitude without constant pressure on the yoke or rudder pedals, like cruise control for attitude.
It takes the pressure off. The handbook also mentions flaperons. A combination.
Yeah, some designs combine the function of flaps and ailerons into one control surface, hence flaperons. They can move together to act like flaps and differentially to act like ailerons.
Clever design. And the handbook stresses knowing your specific aircraft systems.
Absolutely critical. Every aircraft is slightly different. The Airplane Flight Manual or Pilot's Operating Handbook, the AFM or POH, is the official guide for that specific aircraft, and pilots must be familiar with it.
Right, the official manual is key. Now let's dive into some major aircraft systems. The power plant seems like a good place to start.
Makes sense. The power plant provides the thrust. We can focus on reciprocating engines first, the piston engines common in smaller aircraft.
Okay, like a car engine, but for a plane.
Similar principle, yes. Pistons moving back and forth or reciprocating, inside cylinders to turn a crankshaft, which turns the propeller. The handbook mentions both two-stroke and four-stroke designs.
Four-stroke is more common in aviation, right? Like cars.
Mostly, yes. Intake, compression, power, exhaust. The handbook notes two-strokes have a better power-to-weight ratio, which is good, but they're generally less efficient and have higher emissions, limiting their use.
Got it. What about constant speed propellers? How do they work with the engine?
Instead of having a fixed blade angle, a constant speed prop automatically adjusts the pitch of the blades to maintain a specific engine RPM set by the pilot. This is more efficient across different flight phases.
So the pilot sets the desired RPM, and the prop adjusts itself. How does the pilot control power then?
With a constant speed prop, power output is primarily managed using manifold pressure, or MAP. There's a gauge that shows the pressure inside the engine's intake manifold. Opening the throttle increases MAP, which means more fuel-air mixture is going into the cylinders, producing more power.
MEP for power, RPM for efficiency.
Mhm.
Okay. What about fuel delivery? Carburetors versus fuel injection?
Older designs often use carburetors, which mix fuel and air before it enters the cylinders. They can be prone to icing under certain conditions. Fuel injection systems deliver fuel directly into the cylinders or just before them. They're generally more efficient and less prone to icing, but can be susceptible to vapor lock in hot conditions.
Trade-offs there. And the spark. Ignition system.
Aviation piston engines use magnetos for ignition. These are engine-driven generators that create high-voltage electricity for the spark plugs. Crucially, as the handbook points out, magnetos are completely independent of the aircraft's main electrical system.
Independent ignition, a key safety feature, right?
Yeah.
The electrical system fails, the engine keeps running.
Exactly. That's why there are usually 2 magnetos and 2 spark plugs per cylinder redundancy.
Smart design. The handbook mentions detonation. What is that, and why is it bad?
Detonation is like an explosion of the fuel-air mixture in the cylinder rather than a smooth burn. It can be caused by using the wrong fuel grade, overheating, or running too high a power setting with too lean a mixture. It causes extreme pressure spikes and can quickly damage the engine.
So avoid detonation, use the right fuel, manage the engine properly. What about FADEC? Sounds high-tech.
Full Authority Digital Engine Control. It's basically a computer system that manages all aspects of engine performance, fuel flow, ignition timing, prop speed automatically. Optimizes performance, reduces pilot workload. They have built-in redundancy too, more common on turbine engines and some newer piston engines.
Computer-controlled engines. Okay. Let's switch from piston engines briefly. Turbine engines. The handbook mentions compressor stalls.
Right. In turbine engines jets, turboprops the compressor, squeezes the incoming air. A compressor stall happens when the airflow through the compressor blades is disrupted. It can cause noise, vibration, loss of thrust, can be caused by abrupt flight maneuvers, engine damage, or atmospheric conditions like icing.
Airflow disruption in the jet engine. Got it. Moving on from engines, fuel itself is critical. Aviation gasoline, AVGAS.
Yes, the handbook discusses AVGAS grades like 80, 100, and the most common now, 100 LL low lead. It's vital to use the correct grade specified in the aircraft's POH and on placards near the fuel cap. Using a lower grade can cause detonation.
And using car gas is generally a no-go.
Absolutely not unless the aircraft has a specific approval, a supplemental type certificate, STC, allowing it. Car gas has different properties and additives that can harm aircraft engines and fuel systems.
So stick to the approved AVGAS and checking the fuel before flight.
Essential. Pilots need to visually check fuel samples from tanks and the fuel strainer for water and contaminants before every flight. Water in the fuel can cause engine failure.
Water check critical pre-flight step. Okay, other systems. Cabin pressurization. Why do we need that?
At high altitudes, the air is too thin to breathe normally. Pressurization systems keep the cabin altitude, the air pressure inside at a comfortable level, usually equivalent to about 8,000 feet or lower, even when the aircraft is flying much higher. This prevents hypoxia.
Keeps the cabin pressure safe. How does it work, briefly?
It pumps compressed air, usually bled from the engines, into the cabin. An outflow valve regulates how much air escapes, maintaining the desired pressure differential between inside and outside. There are safety valves, too, in case of overpressure.
What if it fails?
A pressurization failure requires a rapid descent to an altitude where the cabin pressure is safe, often involving deploying passenger oxygen masks.
Which brings us to oxygen systems. When are they required?
Regulations require supplemental oxygen for pilots above certain altitudes for extended periods, generally above 12,500 feet for more than 30 minutes, and always above 14,000 feet. Passengers need it above 15,000 feet. But the handbook wisely recommends using it even lower, especially at night, say above 5,000 feet, as vision degrades quickly without enough oxygen.
Better safe than sorry with oxygen. Last system here. Ice protection. How do planes handle ice?
Ice forming on wings and control surfaces is extremely dangerous. It disrupts airflow, adds weight, increases drag. There are different systems. Dicing boots are inflatable rubber strips on the leading edges. Inflating them cracks and sheds accumulated ice.
Inflatable boots to break ice off. What else?
Thermal systems use heat. Some use hot air bled from the engines ducted to the leading edges. Others use electrical heating elements embedded in the wings or propellers, like the thermal wing system mentioned in the handbook. These are generally anti-icing systems, meant to prevent ice from forming in the first place. Proper pre-flight checks of these systems are vital.
Heat or boots to fight ice. Critical for flight safety in certain weather. Okay, let's move into the cockpit. Flight instruments. How do pilots know what the plane is doing? The pitot-static system seems fundamental.
It is. It provides the pressure information needed for three key instruments: the altimeter, the airspeed indicator, ASI, and the vertical speed indicator, VSI. It uses a pitot tube facing forward to measure impact air pressure, and static ports, usually flush on the fuselage, to measure ambient air pressure.
Okay, pitot for impact pressure, static for ambient. How does the altimeter use that?
The altimeter contains sealed aneroid wafers, like little bellows. These expand or contract based on the static pressure measured by the static ports. Lower pressure outside, higher altitude, lets them expand, moving the needles on the gauge. Pilots need to set the current local barometric pressure in the altimeter's Kollsman window to get an accurate altitude reading above sea level.
So you have to tell it the current pressure setting. The handbook gives an example of changing settings between airports,
Yeah.
and it defines different kinds of altitude.
Yes. Indicated altitude is what you read on the dial. True altitude is your actual height above sea level. Absolute altitude is your height above the ground directly below you. Pressure altitude is the altitude shown when you set 29.92 inches of mercury in the altimeter used for performance calculations and flight levels. Density altitude is pressure altitude corrected for non-standard temperature, crucial for performance.
Lots of altitudes. What about the airspeed indicator using the pitot-static system?
The ASI measures the difference between the impact pressure from the pitot tube and the static pressure. This difference, called dynamic pressure, is directly related to airspeed.
And if the pitot tube gets blocked by ice or an insect?
A blocked pitot tube but clear static port means the ASI will act like an altimeter reading higher airspeed as you climb, lower as you descend, regardless of actual speed. Very dangerous. A blocked static port freezes the altimeter and causes errors in the ASI and VSI. That's why pitot heat is so important in potential icing.
Blockages cause serious errors. And the vertical speed indicator, VSI.
The VSI measures the rate of change in static pressure. It has a calibrated leak. When you climb or descend, the pressure inside the instrument case changes slower than the pressure inside the aneroid wafer, causing the needle to show a rate of climb or descent. It lags a bit, but gives trend information quickly. Some newer ones, IVSIs, are instantaneous.
Rate of climb or descent. Okay, those are the pressure instruments. What about gyroscopic instruments?
Gyros use the principle of rigidity in space. A spinning wheel wants to stay aligned in its original plane in precession, where a force applied to a gyro is felt 90 degrees later in the direction of rotation.
Physics principles at work. Which instruments use gyros?
The turn indicator, either a turn and slip indicator or a turn coordinator, shows the rate of turn. The turn coordinator also shows rate of roll. Both have an inclinometer, that little ball in curved glass, to show if the turn is coordinated ball-centered means no slipping or skidding.
Rate of turn and coordination. What else?
The heading indicator, or directional gyro. It's set to the magnetic compass, but doesn't suffer from the compass's turning and acceleration errors. It provides a stable heading reference, but it does drift over time due to friction and needs to be periodically realigned with the magnetic compass.
Stable heading, but needs checking. Modern systems use AHRS.
Yes, attitude and heading reference systems use solid-state sensors, accelerometers, and magnetometers instead of mechanical gyros. Much more reliable and integrated with glass cockpit displays. Provides attitude, heading, rate of turn, and slip-skid info.
Digital gyros, essentially. Now, the good old magnetic compass. Still required, right?
Absolutely. Works based on the Earth's magnetic field. Simple, reliable, needs no power. But it has limitations the handbook details. Oscillation and turbulence, deviation caused by the aircraft's own metal and electronics, variation between true north and magnetic north.
Variation, the difference between true and magnetic north. The handbook mentions the agonic line.
Right. The agonic line is where variation is zero. East or west of it, you have to correct your magnetic heading to get a true heading, or vice versa, using info from aeronautical charts.
And compass errors during flight. Acceleration, deceleration, turns.
Yeah, notorious errors. In the northern hemisphere, accelerating makes the compass indicate a turn to the north. ANDS, accelerate north, decelerate south. Turning errors are most pronounced on north or south headings. UNOS, undershoot north, overshoot south. Pilots learn mnemonics to remember these.
Tricky instrument. There are newer vertical card compasses, too.
Yes, they look more like a heading indicator, easier to read, fewer errors. Still a magnetic compass, though.
One more instrument getting attention. The angle of attack. AOA indicator.
Very useful. Since stalls happen at a critical AOA, regardless of speed, weight, or G-loading, an AOA indicator gives direct information about how close the wing is to stalling. It provides much better situational awareness, especially during maneuvers or approaches, than just relying on airspeed. The handbook highlights its benefits.
Correct measure of stall margin. Sounds valuable. Okay, switching topics, slightly flight manuals and weight and balance. What's the key difference between an owner's manual and an AFM-POH?
An aircraft owner information manual is often provided by the manufacturer, but it's usually generic information, not specific to a particular serial number aircraft, not FAA approved, and not necessarily kept current. The Airplane Flight Manual, AFM, or Pilot's Operating Handbook, POH, is FAA approved, specific to that aircraft, and contains the official operating limitations and procedures pilots must follow. It has to be on board.
AFM-POH is the official required document.
Got it.
Airworthiness certificates.
Shows the aircraft met its original design standards, needs to be displayed in the aircraft. Special flight permits or ferry permits can be issued for aircraft that don't currently meet airworthiness standards but are safe for a specific flight, like to a repair station.
Okay, and what if something minor breaks? Could you still fly? MELs.
Depends. For larger aircraft operated commercially, they often have a minimum equipment list, MEL, approved by the FAA, specifying what equipment can be inoperative while still allowing flight. For smaller aircraft without an MEL, regulations dictate a process to determine if flight is allowed with inoperative equipment, often involving placarding it and having a mechanic deactivate it if necessary.
Procedures for flying with broken gear. Now, weight and balance. Why is this so critical?
Extremely important. The aircraft is designed to fly safely only within specific weight limits and a specific center of gravity, CG, range. Overloading or having the CG too far forward or too far aft drastically affects performance, stability, and controllability. It can make the aircraft unsafe to fly.
Affects everything, so pilots have to calculate it before every flight.
Yes. They need to know the aircraft's empty weight and CG, then add the weight of fuel, pilots, passengers, and baggage, calculating the moment for each item that's weight times its distance from a reference point, datum. They sum the weights and moments to find the total weight and the final CG position, ensuring both are within limits. The handbook shows sample calculations. Even variations in passenger weights matter.
Detailed calculations needed every time. Okay, let's revisit aerodynamics briefly, thinking about maneuvering and stability. How does weight act differently in a descent?
In a straight and level descent, weight still acts downwards, but thrust might be reduced, and the flight path is angled down. Lift doesn't need to equal the full weight anymore, just the component of weight perpendicular to the flight path.
Gotcha. What about stability? Does an aircraft tend to stay on course? Static versus dynamic?
Static stability is the aircraft's initial tendency to return to its original position after being disturbed. Positive static stability means it wants to return. Neutral means it stays in the new position. Negative means it tends to move further away. Dynamic stability is how the aircraft responds over time after being disturbed. Does it return smoothly, oscillate back, or diverge?
Initial tendency versus behavior over time. And there's stability around different axes. Longitudinal, lateral, directional.
Right. Longitudinal stability is about pitch nose up-down stability, primarily influenced by the horizontal stabilizer. Lateral stability is about roll tendency to level the wings, often achieved through dihedral, where the wings angle slightly upwards from root to tip. Directional stability is about yaw, like a weather vane, wanting to point into the relative wind, mainly due to the vertical fin. The handbook compares the fin to a feather on an arrow.
Tail surfaces are key for stability. How do forces change in a turn?
To turn, the pilot banks the aircraft using ailerons. This tilts the lift vector. The vertical component of lift still opposes weight, but now there's a horizontal component of lift pulling the aircraft into the turn.
Horizontal lift pulls it around the corner. What about G-forces or load factor?
Load factor increases in a turn because the wings have to generate more total lift enough to balance weight vertically and provide the horizontal turning force. A steeper bank means a higher load factor, measured in Gs. For example, a 60-degree bank results in a 2G load factor.
Steeper turn, higher Gs. How does that affect stalling?
Higher load factor increases the stalling speed. The wing still stalls at the same critical angle of attack, but because it needs to produce more lift, supporting weight plus the turning force, it reaches that critical angle at a higher airspeed. Stalling speed increases with the square root of the load factor, so in a 2G turn, stall speed increases by about 40%.
Higher Gs mean higher stall speed. Important safety concept. We mentioned turbine engines earlier. Can you briefly list the types?
Sure. The main types are turbojet, pure jet thrust, turboprop, jet engine driving a propeller, turbofan, like most airliners, with a large fan bypassing some air for efficiency and quietness, and turboshaft, jet engine providing power to a shaft used in helicopters.
Different ways to use turbine power.
Yeah.
And they have different key instruments.
Yes. Instead of just RPM and MAP, turbine pilots monitor things like engine pressure ratio, EPR, or fan speed, N1 for thrust, exhaust gas temperature, EGT for engine health, procommuters and turboprops and turboshafts, and turbine speed, N2.
Different metrics for different engines.
Mm.
Let's zoom out to the environment. The atmosphere. Its composition matters.
Mostly nitrogen and oxygen, but those ratios are pretty constant up to high altitudes. What really matters for flight is pressure, temperature, and density.
Atmospheric pressure. We talked about it with the altimeter. How does it change?
Pressure decreases with altitude. This affects engine performance, lift generation, and of course, altimeter readings. Standard pressure at sea level is defined as 29.92 inches of mercury, or 10,013.2 millibars.
And density altitude. That sounds important for performance.
Critically important. Density altitude isn't a physical height, it's a calculated value. It's pressure altitude corrected for non-standard temperature. Hot air is less dense than cold air. High humidity also makes air less dense, so on a hot, humid day, even at sea level, the density altitude might be several thousand feet.
And why does that matter?
Because the aircraft performs as if it were flying at that density altitude. Lower air density means less lift from the wings, less thrust from the propeller or engine, and poor climb performance. Takeoffs require longer runways. It's a major factor in performance calculations, especially at high elevation airports or in hot weather.
The aircraft thinks it's higher than it is on hot days. It affects everything, which leads us to aircraft performance. Takeoff distance.
Lots of factors affect takeoff distance. Density altitude, aircraft weight, wind, headwind shortens it, tailwind lengthens it, runway slope, and runway surface condition. Pilots use performance charts from the POH, like the example in the handbook, to calculate the required distance.
Charts are key. What about climbing? Rate versus angle of climb.
Rate of climb, ROC, is how many feet per minute you're climbing getting to altitude quickly. Best ROC speed, VINAs give the most altitude gain in a given time. Angle of climb, AOC, is how steep your climb path is over the ground-clearing obstacles. Best AOC speed, VINX, gives the most altitude gain over a given horizontal distance. VINX is usually slower than VINUS. Again, factors like weight, density, altitude affect climb performance, and there are charts for this.
Speed for time versus speed for obstacle clearance. Cruise performance.
This is about range and endurance. How far can you fly, or how long can you stay airborne? Depends on fuel load, engine fuel efficiency at a chosen power setting and altitude, aircraft weight, and wind. Pilots use cruise performance charts to plan fuel consumption and flight time.
Planning for fuel efficiency. And landing.
Landing distance depends on approach speed. Faster means longer rollout. Weight, density, altitude, wind, and runway condition. A wet runway significantly increases landing distance due to reduced braking effectiveness and the risk of hydroplaning.
Hydroplaning. Like a car on water.
Exactly. Dynamic hydroplaning occurs when the tires ride on a layer of water rather than contacting the runway surface. It can happen at surprisingly low speeds if the runway is wet enough, resulting in almost total loss of braking. The handbook gives examples of how much landing distance increases with excess speed or a tailwind.
Wet runways need extra caution.
Yeah.
Okay, shifting from the how of flying to the how pilots think. Aeronautical decision-making, ADM.
Hugely important. ADM is about a systematic approach to risk assessment and stress management. Good decision-making is key to safety. The handbook outlines steps for it.
What about risk management?
It's the process of identifying hazards, assessing the risks associated with them, and then deciding how to mitigate those risks. The handbook shows a simple model. Identify hazard, assess risk, mitigate. It's a continuous process.
Proactive safety. The handbook mentions hazardous attitudes.
Yes. 5 common ones that lead pilots into trouble. Anti-authority, don't tell me. Impulsivity, do it quickly. Invulnerability, it won't happen to me. Macho, I can do it. And resignation, what's the use? Recognizing these in yourself is the first step. The handbook provides antidotes for each. For anti-authority, the antidote is follow the rule. They are usually right.
Recognizing mental traps. What about pressures?
Pilots face internal pressures like wanting to get home, prove themselves, and external pressures like passenger expectations, schedules. Learning to identify and manage these pressures is vital to avoid making rushed or risky decisions.
Internal and external factors. Human factors like fatigue also play a role.
Absolutely. Fatigue, complacency, stress. They all degrade pilot performance and decision-making. Recognizing your own condition is critical. The IMSAFE checklist is a good tool for this. Illness, medication, stress, alcohol, fatigue, emotion eating. Are you fit to fly?
IMSAFE checklist, good personal check. Are there structured models for making decisions in flight?
Yes, the handbook presents several. The 5 Ps, plan, plane, pilot, passengers, programming, help pilots review critical areas before and during flight. The 3P model, perceive, process, perform, is a continuous loop. Perceive the situation, process its impact, perform the best course of action. It often uses a care checklist, consequences, alternatives, reality, external factors, during the process step.
Perceive, process, perform, care.
Any others? The decide model is another. Detect a change, estimate the need to react, choose a desirable outcome, identify actions to achieve it, do the action, evaluate the effect. These models provide structure, especially under stress.
Structure helps under pressure. And using resources.
Key part of ADM. Internal resources are your own knowledge and skills. External resources include air traffic control, weather briefers, checklists, even passengers who might help with tasks like spotting traffic. Good communication is vital.
Use everything available. Now let's talk about the pilot themselves, aeromedical factors, medical certificates.
Most pilots need an FAA medical certificate to fly, demonstrating they meet certain health standards. Glider and balloon pilots are exceptions, and sport pilots under certain conditions. But even with a certificate, the pilot is ultimately responsible for not flying if they know they have a disqualifying medical condition.
Pilot's responsibility first. What about hypoxia, lack of oxygen?
A major threat, especially at altitude. It impairs judgment, coordination, vision. Symptoms can be subtle and insidious, maybe euphoria, feeling warm, headache. That's why oxygen rules exist, and why using oxygen even below the required altitudes is smart. Treatment is simple. Use supplemental oxygen and/or descend.
Sneaky danger. Ear and sinus problems.
Changes in air pressure during climbs and descents can cause pain if the eustachian tube connecting the middle ear to the throat doesn't open properly to equalize pressure. Same for sinuses. Flying with a cold can make this much worse and potentially damaging. Valsalva maneuver, pinching nose and gently blowing, can help equalize pressure.
Pressure equalization is key. Spatial disorientation. Losing your sense of up and down.
Very dangerous, especially if you fly into clouds or lose visual references. Your inner ear balance system can be easily fooled without visual cues, leading to powerful illusions. The handbook describes several, like the leans, inversion illusion, feeling you're tumbling backwards during a climb, or illusions caused by sloping runways or featureless terrain. Trusting your flight instruments is the primary way to overcome this.
Trust the instruments, not your feelings. Fatigue.
Big factor in aviation accidents. Acute fatigue is short-term tiredness. Chronic fatigue builds up over time, much more serious, degrades performance significantly. Proper rest is essential.
Rest is critical. Decompression sickness, the bends.
Usually associated with scuba diving, nitrogen absorbed under pressure comes out of solution as bubbles if pressure decreases too rapidly. It can happen after diving if you fly too soon, or potentially during rapid decompression at very high altitudes. The handbook shows wait times recommended after diving before flying.
Diving and flying don't mix immediately. Vision is obviously key. Day versus night.
Day vision uses cones in the retina, good for color and detail. Night vision relies on rods much more sensitive to low light, but poor on color and detail. There is also a night blind spot right in the center of vision because cones are concentrated there and rods aren't, so at night you need to scan, looking slightly off-center to see things clearly. It takes time for eyes to adapt to darkness, too.
Night vision needs different techniques. What about technology like SVS and EVS?
Synthetic vision systems, SVS, use GPS and database information to create a 3D graphical depiction of the terrain, obstacles, and runway environment right on the flight displays. Enhanced vision systems, EVS, use infrared cameras to see through haze, fog, or darkness, displaying the image on a screen. Both significantly improve situational awareness, especially in low visibility or at night.
Technology enhancing side. Okay, let's move to the environment outside the plane. Aviation weather. Why is it so important?
Weather is probably the single biggest factor affecting flight safety and planning. Understanding weather patterns and hazards is absolutely critical for pilots.
Where does weather start? Global circulation.
Large-scale patterns, yes. Uneven heating of the Earth drives global circulation cell. Trade winds, westerlies. The Coriolis force, due to the Earth's rotation, deflects these winds. The handbook shows these basic patterns.
Big picture stuff. What about local winds?
Smaller scale things like sea breezes, wind blowing from sea to land during the day, and land breezes, opposite at night. Also, valley winds blowing upslope during the day, mountain winds blowing downslope at night. These can significantly affect airport operations near coasts or mountains.
Local terrain matters. Turbulence.
Caused by disruptions in airflow. Mechanical turbulence is from friction with the ground or obstacles like buildings or mountains. Convective turbulence is from uneven surface heating causing rising air currents, often found in or near thunderstorms or cumulus clouds. Wake turbulence is from those wingtip vortices generated by other aircraft, especially large ones.
Different causes for bumpy air, stability of the atmosphere.
Stable air resists vertical motion. Unstable air encourages it. This depends on the temperature lapse rate, how quickly temperature decreases with altitude compared to the adiabatic lapse rate, which is the rate air cools as it rises and expands. Unstable air leads to cloud development, turbulence, thunderstorms. Stable air often means smooth conditions, but also haze or fog if moisture is present.
Stability affects clouds and bumps. Moisture? Dew point.
Dew point is the temperature air must be cooled to become saturated. When temperature and dew point are close, you get dew, fog, or clouds. Frost can form on aircraft surfaces if the temperature is below freezing, and dew point is also below freezing. Frost disrupts airflow just like ice. It must be removed before flight.
Frost is a hazard too. Clouds themselves.
Clouds are visible moisture water droplets or ice crystals. They're classified by altitude, low, middle, high, and appearance, like cumulus, puffy, stratus-layered cirrus wispy. Clouds with vertical development, like cumulonimbus, indicate instability and are associated with turbulence, icing, and thunderstorms. The handbook shows the basic types.
Clouds tell a story about the air. Air masses and fronts.
An air mass is a large body of air with fairly uniform temperature and moisture. A front is the boundary between two different air masses. Cold fronts, warm fronts, occluded fronts. They bring changes in wind, temperature, pressure, and often significant weather, like clouds, precipitation, and storms.
Fronts mean weather changes. Thunderstorms seem like the biggest hazard.
Definitely among the most dangerous. They contain severe turbulence, hail, lightning, heavy rain, icing, strong updrafts and downdrafts, including microbursts, intense localized downdrafts that can be catastrophic near the ground. Tornadoes can also form. Pilots give thunderstorms a very wide berth. Pressure changes rapidly near them too. Lightning can damage aircraft electronics or structure.
Avoid thunderstorms at all costs. Okay, pilots need to know the weather. How do they get this info? Weather services?
Lots of resources. Starts with observations. Surface observations, or METARs, give current conditions at airports. Upper air observations use weather balloons. Radar shows precipitation. Satellites show cloud cover and systems.
METARs, those coded reports.
Yes. They look cryptic, but have a standard format. Station ID, time, wind, visibility, current weather phenomena, rain, snow, fog, sky condition, cloud layers, temperature, dew point, altimeter setting, and remarks. The handbook breaks down how to decode them. Pilot reports, or PIREPs, are also crucial actual conditions reported by pilots in flight.
Reports from the ground and the air. What about forecasts?
Several types. Terminal aerodrome forecasts, AMFs, predict conditions at specific airports, usually for 24-30 hours. Aviation area forecasts, FAs, cover larger regions, useful for en route weather. Winds and temperatures aloft forecasts, FB, predict wind direction, speed, and temperature at various altitudes.
Forecasts for airports in larger areas. What about in-flight advisories for hazard?
Yes, airmets, sigmets, and convective sigmets. Airmets advise of moderate icing, moderate turbulence, sustained surface winds of 30 knots or more, or widespread IFR conditions. Sigmets cover non-convective severe conditions like severe icing, severe turbulence, dust storms, volcanic ash. Convective sigmets are specifically for thunderstorms lines, embedded, or widespread areas.
Warnings for different levels of hazardous weather. How do pilots decode the winds aloft forecast, FB?
It's a coded format. First two digits are wind direction, true north. Next two are speed in knots. Then temperature in Celsius. Special rules apply. If direction is over 36, subtract 50 and add 100 to the speed for speeds over 100 knots. Temperatures above 24,000 feet are assumed negative. The handbook shows how to decode it.
Need the decoder ring for that one. Other ways to get weather.
Pilots get briefings from flight service stations, FSS, or online sources before flight. In the air, there's HIWAS, Hazardous In-Flight Weather Advisory Service, broadcast over VORs. And increasingly, data link weather products like FISB provide graphical weather like NEXRAD radar imagery and METARs right in the cockpit. But NEXRAD shows where precipitation was, not where it is now, so there's a time lag.
Lots of ways to get weather info, but need to understand limitations like radar lag. Okay, airport operations and airspace. Markings and signs.
Essential for ground navigation. Runway markings, centerline, edge lines, designation numbers, taxiway markings, centerline, hold short lines, airport signs, location, direction, mandatory instructions like holding short of a runway. The handbook has extensive examples. Getting lost on the ground can lead to dangerous runway incursions.
Follow the signs and lines. Radio communication.
Critical for safety in controlled airspace and at towered airports. Standard phraseology is key to clear communication. The phonetic alphabet, Alpha, Bravo, Charlie, is used for clarity. There are also standard light gun signals from the tower if radio communication fails.
Standard words and backup light signals. Wake turbulence, we mentioned vortices earlier. How do pilots avoid it?
It's strongest behind heavy aircraft that are flying slow and clean, flaps gear up, like on takeoff or approach. Pilots need to stay above the preceding aircraft's flight path and land beyond its touchdown point, or take off before its rotation point and climb above its path. Wind can make vortices drift. A light quartering tailwind is often considered the worst case for keeping vortices over the runway.
Stay above and beyond the big guys. Runway incursions, aircraft ending up on a runway without clearance. How to prevent?
Big safety focus. Prevention involves clear communication, reading back instructions, writing down complex taxi clearances, using airport diagrams, being especially vigilant at complex intersections or closely spaced runway thresholds, and always obeying hold short instructions explicitly. Some airports have engineered materials arresting systems, EMAS, soft ground at the end of runways to stop overruns safely.
Vigilance on the ground is key. Now, airspace. Controlled versus uncontrolled.
Controlled airspace, classes A, B, C, D, E, means ATC has some level of authority and responsibility. Requirements like radio communication, transponders, specific pilot qualifications, and weather minimums vary by class. Uncontrolled airspace, class G, means ATC has no authority or responsibility. VFR pilots are generally on their own for traffic separation.
Different classes, different rules. Class A is high altitude.
Yes, Class A is from 18,000 feet up to flight level 600. All flights must be under Instrument Flight Rules, IFR, and in contact with ATC.
Class B is around the busiest airports.
Right. Solid blue lines on charts. Requires specific ATC clearance to enter. Usually has multiple layers like an upside-down wedding cake. Strictest VFR weather minimums, 3 miles visibility, clear of clouds.
Class C and D are around smaller towered airports.
Yes. Class C, solid magenta lines, requires two-way radio communication before entering. Class D, dashed blue line, also requires two-way radio contact. Both generally surround airports with operational control towers.
Class E is controlled but can be widespread.
Very widespread. It's controlled airspace that isn't A, B, C, or D. Can start at the surface, 700 feet AGL or 1,200 feet AGL. Below 10,000 feet, VFR minimums are typically 3 miles visibility, 500 feet below, 1,000 feet above, 2,000 feet horizontal from clouds.
And Class G is uncontrolled.
Yes. Usually found below the floor of Class E airspace away from airports. VFR minimums are generally lower, especially during the day below 10,000 feet, often 1 mile visibility clear of clouds.
Layer cake of rules. What about special use airspace?
Areas where flight activities must be confined or where limitations are imposed. Includes prohibited areas, no flight allowed, restricted areas, flight restricted, need permission, warning areas like restricted but over international waters, military operations areas, MOAs, military training, VFR flight allowed with caution, alert areas, high volume of pilot training or unusual activity, and controlled firing areas, not charted, activity stopped if non-participating aircraft approach.
Areas to be aware of or avoid. TFRs, temporary flight restrictions.
Set up for specific events like VIP movements, major sporting events, disaster relief, wildfires. Very important to check NOTAMs for TFRs. Flying into one can have serious consequences.
Check NOTAMs for temporary restrictions too. Okay, final major topic, navigation. Getting from A to B, basic methods.
The classics are pilotage navigating by reference to landmarks on the ground and dead reckoning calculating position based on heading, airspeed, time, and wind. Radio navigation uses ground-based stations or satellites.
Landmarks, calculations, or radios. What about charts?
Aeronautical charts are the pilot's roadmap. Sectional charts are most common for VFR flight, showing airports, navigation aids, airspace, topography, obstacles. VFR terminal area charts, TACs, provide more detail around busy Class B airspace. World Aeronautical Charts, WACs, cover larger areas with less detail, used for higher speed aircraft or longer flights.
Sectionals are the main VFR map. Using the magnetic compass for direction requires corrections, variation and deviation.
Yes. We mentioned variation, the difference between true north and magnetic north found on the chart. Deviation is the error caused by the aircraft's own magnetic fields. A compass correction card near the compass tells the pilot how much deviation error exists on different headings.
So you go from true course from the chart to magnetic course, applying variation, to compass course, applying deviation, to figure out what heading to actually steer.
Exactly. And then you also have to account for wind. Wind correction angle adjusts your heading to counteract drift, and wind affects your ground speed, how fast you're actually moving over the ground. Headwinds slow you down, tailwinds speed you up.
Lots of calculations for dead reckoning. What resources help plan a cross-country flight?
The Chart Supplement US, formerly Airport Facility Directory, provides detailed info about airports, nav aids, services. NOTAMs are critical for temporary changes. The sectional chart itself has lots of info in the legend and margins. Pilots typically create a flight log noting checkpoints, headings, distances, estimated times, and fuel calculations. The handbook shows an example log.
Planning is key. What about radio navigation? VORs.
VOR stands for Very High Frequency Omnidirectional Range. It's a ground-based station transmitting signals that allow pilots to determine their bearing from or to the station. Pilots tune the VOR frequency and use the Course Deviation Indicator, CDI, in the cockpit to fly along specific radial lines extending out from the VOR. It works line of sight, so range is limited by altitude.
Flying along electronic pathways. What about distance measuring equipment, DME?
Often co-located with VORs, then called a VORTAC, DME measures the slant range distance, the direct line, not ground distance between the aircraft and the station. Useful for knowing your position along a VOR radial.
Bearing from VOR, distance from DME, RNAV, area navigation.
RNAV allows pilots to navigate directly between user-defined waypoints, rather than having to fly directly to or from ground stations like VORs. Early RNAV systems used VOR-DME signals to compute courses to virtual waypoints. Modern RNAV heavily relies on GPS.
GPS Global Positioning System. How does that work for planes?
Uses signals from a constellation of satellites. The receiver calculates its distance from multiple satellites, pseudorange, to determine its position latitude, longitude, and altitude. You need signals from at least 4 satellites for a 3D position.
Satellites triangulate position. What is RAIM?
Receiver Autonomous Integrity Monitoring. The GPS receiver itself continuously verifies the integrity of the satellite signals it's receiving. If it detects a potential error, it alerts the pilot. Important for using GPS for instrument approaches.
Built-in error checking. Any limitations to GPS?
GPS altitude isn't always as accurate as pressure altitude from an altimeter, and signal blockage can occur near terrain or buildings. Fundamentally, the handbook reminds us GPS is a tool. The pilot is still ultimately responsible for navigation and situational awareness. Sometimes VFR waypoints, not associated with ground nav ads, are published on charts for use with GPS or RNAV.
GPS is a powerful tool, but pilots still in command. Wow, we've covered a huge amount of ground or maybe airspace.
We really have. From the rules of the road set by the FAA through the physics of flight, the nuts and bolts of aircraft construction and systems, the instruments pilots rely on, the critical aspects of weather and navigation, and the human elements of decision-making and medical fitness. It's a lot.
It truly underscores the breadth of knowledge required just for the fundamentals of flying, all packed into this one handbook. What stood out to you as particularly interesting or maybe surprising looking through it again?
Maybe just the sheer interconnectedness of it all. How a change in density altitude affects not just takeoff performance, but also engine power and climb rate. Or how understanding atmospheric stability helps predict turbulence and cloud types. It's all linked. Also, the emphasis on redundancy, dual ignition, backup instruments, multiple decision-making models highlights the focus on safety.
Yeah, that layered safety approach really comes through. And hopefully this deep dive gives you, our listeners, a solid shortcut to being pretty well informed about these aviation essentials. It might change how you think next time you're at an airport or looking up at a plane.
Absolutely. It's a complex world, but understanding the basics makes it less mysterious and maybe even more fascinating.
So here's a thought to leave you with. Considering all these layers, the regulations, the engineering, the pilot training, the weather forecasting, what single aspect of aviation safety do you think is the most critical linchpin holding it all together? Something to ponder.
Good question. Lots of potential answers there.
Indeed. Let us know if you have questions or other topics you'd like us to dive into. Thanks for joining us on The Deep Dive.
See you next time.